So hello everybody. So I've actually changed the title of my talk. I'm going to be a bit more general, and I'm going to talk about electric field manipulation of perpendicular magnetic anisotropy and other actually magnetic properties in platinum cobalt oxide multilayers. There's a lot of noise. So I need to acknowledge the work of my postdoc Alain Fassatoui. It's too much noise. That was funded by the DARPA project, and then Christina Balan, my PhD student, that is funded by Marie Curie Actions. And this is a collaboration between our group at Institut Néel and Spintech Laboratory. So electric field manipulation of magnetic properties have been actually found, pioneered in our group by my colleague Dominique Givor in 2007, and they showed that by thin iron platinum and iron palladium layers, that by applying electric field, this time in a liquid electrolyte, they could change the magnetic anisotropy by a few percent. A bit more recently, we found also this time using a solid gating, that in platinum cobalt alumina we could change the different magnetic energies in order to switch with an electric field the platinum cobalt alumina from a system in a state in which you have skyrmions to one in which the skyrmions were annihilated, and we call this the switch skyrmion switch device. So all this until very recently. So this voltage manipulation with electric field was associated to electronic properties, so accumulation or depletion of electric charge at the Fermi level, and this gives rise to quite small variations of the perpendicular magnetic anisotropy, just a few percent. But more recently, so magneto-ionic effects have been shown to give rise to much larger variations of magnetic anisotropy, and I show here in particular the work of the Beach group on platinum cobalt bilayers covered by a gadolinium oxide multi-layer that is known to be an oxygen ionic conductor. In this case, they managed to show that they can change anisotropy by an order of magnitude larger than with electronic effects or more. So that the magnetic anisotropy can be shown, so the magnetization can be switched to outer plane to in plane, and then in the reversible way back to outer plane. Well, other groups have been showing that these effects always using gadolinium oxide layer. The effect was shown to be non-volatile, so when you remove the electric field, the sample state, the magnetization stays the same. The effects are reversible, and this was associated to the migration of oxygen ions through this gadolinium oxide layer that is, as I say, ionic conductor, so that the chemical structure of the interface, the top cobalt interface is modified. So how can we explain this? Oops, so I go back to something that has been introduced this morning already. What we know about PMA, perpendicular magnetic anisotropy, in this kind of trilayers, platinum cobalt covered by an oxide. This was the work of the Spintech group a while ago, so 10 years ago. So they showed that, okay, there is a strong, of course, there is a strong contribution to the anisotropy coming from the platinum cobalt interface that we know, but there is also a contribution coming from the top interface, the cobalt oxide interface. And this contribution, depends on the state of oxidation of the cobalt interface. So what I showed in the case of, for example, platinum cobalt 0.6 nanometers covered by aluminum, by oxidizing it differently, that if they don't oxidize it, they have in-plane anisotropy. If they start oxidizing, then the magnetization goes out of plane, so the anisotropy increases. They get a maximum, and then they go to what they call the over-oxidized state. Then the anisotropy decreases, and then you can get to multiple domain state or in-plane state. And what we showed by XPS measurements is that this maximum anisotropy corresponds to the situation in which the cobalt-aluminum and cobalt-cobalt bonds are totally substituted by cobalt dioxygen. So we have that so in this position, the last cobalt layer is totally covered by oxygen. So in this case, we understand why the oxygen migration induced by electric field can change the anisotropy. So what actually we had, as I said in the previous works, people used this gadolinium oxide that is an ion conductor. We had a slightly different approach. So we used platinum cobalt oxide tri-layers in which we change the oxide, the metal. It could be, we study actually aluminum, magnesium, and terbium. We pattern it. So why do we use this multi-layer? First of all, because of the large magnetic anisotropy, because of the large Dzyaloshinskii-Moriya interaction that induces chiral Néel walls, as we all know, and skyrmions, of course. And actually, we have been busy for many years in collaboration with André Thiaville in Paris to work on to figure out the domain wall dynamics in this kind of systems that are strongly modified by the presence of DMI. But I'm not going to talk about DMI really today. So as I said, so we start with platinum cobalt alumina, then we cover it, that is patterned, we cover it with 10 nanometers of zirconium oxide or hafnium oxide that are both well-known high-K dielectric that are also good ionic conductors, and then we pattern on top platinum electrodes. Okay, so then, I just show you some examples of the results obtained the last couple of years. So the first system is platinum cobalt aluminum oxide with zirconium oxide as a dielectric layer and platinum electrodes. So in this case, we start with a sample, so it's 0.6 nanometers of cobalt. In the pristine state, we have these square loops with large perpendicular anisotropy. If we apply a positive voltage, you can see that we can reduce the magnetic anisotropy, actually in a reversible way. I show it here. So if you apply the opposite voltage, so the negative voltage, then we can go back to the initial large coercive field. So what you observe is that this effect is non-volatile. So if we remove the voltage, the gate voltage, then the state stays the same, the magnetization stays the same. And as you see here, it's reversible. So we interpret this because of the non-volatility. We interpret it in terms of migration of oxygen ions within the zirconium oxide layer down to the aluminum cobalt interface. And since we started from an under-oxidized state, the application of a of a positive voltage drives oxygen away from the interfaces, and then we have a decrease of the anisotropy, and the opposite for a negative voltage where we start oxidizing the sample and therefore increasing the anisotropy. So for the same sample, so we see, but we also show that the effect, the effect of the gating, and therefore the decrease of the anisotropy, changes also the reversal mechanism in these strips. So you can see that here in the initial state, so in the pristine state before applying the electric field, you have that the reversal occurs by, these are just Kerr images. The reversal occurs by the nucleation of a few domains and the propagation of domain walls. You can see here the domain walls within the electrode area that are this white part. And then if you apply the electric field, this time 2 volts for 5 seconds, then you can see that now the procedure, the reversal occurs via nucleation of reverse domains, and then their density increases as the time application of voltages increases. And then if you apply the opposite voltage, then we go back slowly to the initial reversal mechanism due to propagation of domain walls. Okay, then I just wrote down here that the electric field efficiency is very large in this system, and it's actually as the same order of magnitude that was obtained by the Beach group at high temperature, while all these measurements are carried out at room temperature. Another system on which we worked, and so we saw that this phenomenon also works for terbium oxide, So it's platinum cobalt terbium oxide. In this case, the thickness of the cobalt is it's a bit thicker, the cobalt. And the initial state, the magnetization lies in the plane. So it's this black cycle. And then applying a negative voltage, you can push the magnetization out of plane. And then if you apply the opposite voltage, then you can go back in plane. And then you have this intermediate state with this, what we call this butterfly loop, in which that reveals the presence of stride domains. And you can see here the MFF images that show the presence of some stripe domains and also of some skyrmions. And then if you apply a voltage, then you can go to the saturated state. And so you can reversibly change from a state with skyrmions to a state without skyrmions by applying electrical voltage. And as I said, this effect, again, is non-volatile, and as I showed, is reversible. Yes, so this was just to show that the PMA variation, but the PMA varies as a function of time, and that this can be actually tuned quite finely. For the same system, you start from a saturated state, you apply the electric field for a certain time, and you see here the appearance of these stride domains that reveal that we are now close to the reorientation transition with a certain stripe domain size. And then if you apply the voltage for another time, so this time to 30 seconds long, you have a smaller dimensions. And this is related to the fact that the period of the stripes is related to domain 1 energy, and the domain 1 energy is decreased via the change of the magnetic anisotropy induced by the electrical gating. Okay. So up to now, actually, I showed you only the variation of the anisotropy in this region, so between the under-oxidized and the maximum here. But we showed that actually we can realize a much larger variation of anisotropy, in this case platinum cobalt terbium. We can go from the under-oxidized state here, actually it was from over-oxidized state, up to the maximum, and then from the under-oxidized state, and vice versa. But also here I just show the variation of the anisotropy, of the coercive field as a function of time during the application of a constant voltage. And here, the way we did it, we just have one hysteresis loop taken every 5 seconds, and then we just plot the coercivity as a function of time. And so here we did it with several voltages. So let's take first, for example, this one, the 1.8. You can see at the beginning a very fast variation of the coercivity, so of the anisotropy as a function of time, following by a slower decay. Decay of the anisotropy beyond the maximum. And then what you can see is that as you increase the voltage, of course, you accelerate the process so that the switching occurs faster. But I don't have the time to show you, but we can, by a very simple model, we can model this variation of the anisotropy, this fast variation at the beginning, and this lower variation after the maximum, just by assuming a parabolic variation of the anisotropy, and then you see, this is a parabolic variation of anisotropy and a logarithmic variation of the oxidation rate as a function of time. Actually, this is in our paper here. Okay, the same kind of variation, we obtain it also for platinum, cobalt, aluminum. In this case, we just measured the switching time needed to go from the over-oxidized state to the maximum and vice versa. As a function of, what is this? Okay, so as a function of the applied voltage, should I continue or? What is this music? Ah, it's next door. Ah, okay, bon. So as you can see here, for example, in the case of the oxidation, is that by increasing the applied gate voltage, you can change the variation. You can change the switching time by 5 orders of magnitude. So we start with 1 volt. We have 400 seconds to switch the magnetization. If you're down to 6.5 volts, we can go down to 10 milliseconds. I just want to add a comment on the fact that obviously we are this is not a fast way to switch in magnetization. We saw this morning from Pietro that you can obtain much faster switching by spin-orbit torque. But this is, if we think of application, the application will be different, will be non-volatile something, or could be actually, Vincent just talked about the possibility to use this kind of phenomenon for neuromorphic computing or neuromorphic kind of devices. Okay, so as I said, the switch can be changed. The switching time can be changed considerably by increasing the voltage because of this exponential variation of the switching. That is related actually to the exponential variation of the spin of the drift velocity of ions within the dielectric layer. So you can see here, this was predicted theoretically a long time ago by Mott actually, and then taken also in this paper is explained here. And what they show is that this is a theoretical model that they say for beyond a certain threshold electric field, the spin drift velocity of ions would change exponentially with the voltage. And then from that, we can from this expression, you can extract the activation barrier for ions to jump between one valence state, vacuum state to another. And then from this slope, we actually get a value for this energy barrier about 1 electron volt that is consistent with what is found in the literature. Okay, the last part I wanted to, the last thing that I wanted to show is that by changing, so I showed you that we are changing with electric field, we can tune magnetic anisotropy. And as we know, domain wall speed depends on domain wall energy, depends on anisotropy. And so here I show in the case of platinum cobalt terbium that the domain wall speed, in this case, driven by a magnetic field, can be strongly changed as a function of gating. So in this case, so this is the electrode region. So the domain wall velocity is the same outside and below the electrode. If you apply gating, this is this negative gating, you can see that they go much faster here. And then if you apply the opposite gating between below the electrode, the domain walls practically don't move. And this is so these movies are in real time. So the domain wall speeds are very slow, microns per second. So it's the so-called creep regime, where the domain wall energy, the domain wall speed depends on domain wall energy exponentially. So by changing very slightly the anisotropy, you can have an exponential change of the domain wall velocity. So we have about a factor, I think, 15 of domain wall velocity between pristine and gated. Doesn't work anymore. Yes. But we were interested to see whether we could have a larger change of domain velocities, or also where domain walls go fast. And so far, actually, there are very few papers in the literature considering the high speed regime. So I found this work here, in which you can see that effectively, even for decent domain wall speeds, so large fields, you can have some maybe 50% variation of the domain wall speed by applying a gate. In this case, the variations are much lower. The maximum variation, anyway, you have them in the creep regime. And then there is this recent paper by Stuart Parkin group. In this case, these are spin orbit torque driven domain wall motion. In his classical SAF system with cobalt nickel bilayers coupled through ruthenium, in which he shows that because of what he calls the exchange torque, he has maximum domain wall velocities where you have compensated magnetization in the two layers. And then what he does, this time using ionic liquid, so he oxidizes part of the top layer. So the magnetization is no longer compensated, and then he has this variation of the domain wall speed. What we did is actually different. So we have a platinum cobalt terbium layer, so in which, as you know, cobalt and terbium are aligned antiparallel. So this system, so it's a ferrimagnet. The magnetization is pretty low. we measured in the pristine layer a compensation temperature of 100 K and a large anisotropy with an in-plane saturation field of almost 2 Tesla. So what we have, so before applying the gating, you see that the volume velocity, this time driven by field, is very, very low. Even if with 300 millitesla, we have 20 meters per second. So how do we explain this very small speed? We explain it by saying that, okay, you have a very strong depending field. The depending field depends actually on the domain wall energy divided by the magnetization. Domain wall energy is large because of the large anisotropy, and the magnetization is small because we have a ferrimagnet, so we have this very, very small increase of the velocity. When we apply the gating, that actually pushes oxygen ions towards the interface, but towards the magnetic layer, then what you observe by Kerr microscopy is, first of all, that below the electrodes we have this decrease of the in-plane saturation field, and then in the domain velocity you can see that so by increasing keep increasing the gating, we have a decrease of the tipping field, and then eventually the recovery of this high domain volume velocities, those that we accept for system with high DMI and the current Néel walls. So how do you explain this? So what we think is that by gating we start oxidizing partially the terbium layer, and this we expect therefore the magnetization to increase. We see that the anisotropy increases, therefore the deepening field decreases, and then we can recover these high speeds. So the idea is, okay, we have in this case passing from a system in which we are essentially having domain walls in the creep regime to domain walls in the field in the flow regime. We have this huge variation of the domain wall velocity. How many minutes do you have? Okay, so it's fine. Yeah. So the idea. So the problem about this kind of solid state device is that. So we had very small electrodes. The electrodes in this case they were, I think, 10 by 20 microns, but we went down also to 1 micron, 500 nanometers electrodes. So once you have modified your structure below the electrode, there is practically no way to, no technique to look what is happening, especially below 10 nanometers of dielectric layer. So we have to propose a model. So what we propose, okay, the magnetization increases, and then we measure the PMA that decreased. So it turns out that many years ago we had measured this platinum cobalt terbium bilayers that we never published actually, in which we saw that by decreasing the contribution of the terbium in this bilayer, so we decrease the composition of the terbium, we have an increase of the magnetization and a decrease of the anisotropy. That is exactly the behavior that we see in our gated systems. And then at the same time, you see that as you decrease the terbium thickness, you have this increase of the domain wall speed. So this sort of confirms that the model that we proposed is correct. So the idea is simply that we go away from the compensation of the cobalt and the terbium moments. I think it's finished. Yes. Okay, so up to now I showed you that we can modify the perpendicular magnetic anisotropy, the domain wall velocity is a consequence. I just asked, well, I had this slide yesterday saying, well, what about the DMI? Because there are systems in which we know that we do DMI. I don't show it today, but we did several works on DMI in these systems. And in particular here in this bilayer, we also showed that by increasing so by gating the system, we have a decrease of the DMI field. So as I say now, we don't have a means to measure the magnetization and directly measure the DMI, because from the HDMI field, I need the magnetization. So we just did micromagnetic simulations from which we found out that there is a strong variation of the DMI as well associated to the gating. And I don't have time. We have a model, but maybe I don't discuss it today. And then what about the first two systems that I showed, the platinum cobalt oxide systems, in which I showed that there is a variation of the anisotropy due to the change oxidation of the state. We didn't measure actually the DMI field in those samples, but I just wanted to remind you what we published a while ago in 2019 in platinum cobalt aluminum oxide and gadolinium oxide, in which we showed a very nice correlation between the variation of the anisotropy and of the DMI as a function of the oxidation. So as a function of oxidation of these bilayers, we have a variation of anisotropy and DMI that is following the same sort of parabolic curve. So I expected also by gating, we should have a variation of the DMI. And with this, I think that I finish. So I've shown you, but I think that so strong electric field effects in this kind of platinum cobalt oxide layers, so using zirconium oxide dielectric layer. We actually used also hafnium oxide dielectric layer and also some yttrium doped zirconium oxide more recently. I've shown you that the variations are large, they are non-volatile and reversible. It applies to different kinds of systems. And then we interpret this as an oxygen migration, modifying the rate of oxidation of the top cobalt interface. As I said, the effect is slow. Well, depends on what you call slow, but they are slow. But we also showed that they are largely tunable, and you can get. I'm pretty. I mean, it will never get to a nanosecond. You need to move, when you move atomic species, you will never get to nanoseconds. But we can probably decrease it by still in the microsecond regime. And then I showed you also that domain Waltz velocity can be strongly modified by magneto-ionic effects. Thank you very much.
Very nice talk. So in your system, how much does the oxygen move under gating, the distance it actually travels? Because that would obviously influence the speed, because people in memristors have shown they could get sub-nanosecond when it's only moving across atomic distance. So how far you have to travel will be very important.
They have to travel very fast. I mean, what you know, okay. The thing is, the oxygen is already within the zirconium oxide, okay?
Yeah.
So the oxygen that is close will move very little. But if you want to, the problem is, I think we calculate at some point that we need, I think the equivalent, we need very little oxygen to change the anisotropy, the equivalent of, you know, less than 1 nanometer anyway, 0.3 nanometer. So the other thing is, okay, the oxygen that is moved, it comes from the air, okay? So it has to come from the air and to go across the zirconium oxide layer. So sorry, what I said before doesn't make sense, because in the end, the oxygen that moves is the one that comes from the air and has to move from vacancy to vacancy. It's not the oxide that is inside already in the system. So it's pretty thick.
Yeah.
And then for the platinum cobalt terbium oxide, it's even worse. This is why we need relatively long times, because I showed you it's like 400 seconds for 10 volts, because then it had to go through the zirconium oxide. We have an aluminum that was there for protecting the layer. And actually, I don't show it here, but we did XPS measurements that show that the aluminum oxide, initially it's partially oxidized, and we see that after the gating is only 1 peak, so it's totally oxidized. And then you have the terbium oxide, so it's pretty thick. And this is why the times are so short.
Right, and that may also lead to some irreversibility. It's sometimes hard to get 100% reversibility, right? They're largely reversible, but not. It's very difficult to have 100%.
But that we don't really know. But I suppose there must be some charging at some interface that is such that, I mean, if you call it reversible with the same voltage, no. But reversible in the sense that we can go back to the same, but that with a different time or a different. Actually, I think I have. Yeah. So, but you see the reversibility. Of course, since you are really changing an interface, you don't have perfect reversibility, but after I think we did maybe 20 cycles, and you can see that you have some reversibility, but in any case you can change from strongly the velocity, and yeah.
Yes, thank you.
Okay.
Thank you for the very interesting talk. I wonder whether, besides the effect of the voltage gate on the effective anisotropy, which changes the Pinning energy barrier, the domain wall energy, domain wall width, is there any effect on the damping of the system? Have you measured, have you know if there is an effect? Because this will alter all the velocity response too.
We haven't done, because the problem is that measuring the damping is not so easy. And then measuring the damping under an electrode, actually, the only times that we manage to measure damping is by, by domain wall speed measurements in a sample that is very little, as you know, very little creep regime, so that you manage to have the slope of the flow regime, and then in this case, but in this case, it's of course, I would expect a change of the damping, but I don't know how to measure it actually.
So, when we go back to this, so we go to the coffee break, maybe you can ask Stefania.